Excellent, excellent. Well, greetings, everyone. I want to thank our speaker of today's seminar, Ekansh Jauhari, who's coming from the University of Florida to tell us about distributional and intertwining invariants of manifolds. So welcome, Ekansh.
Thank you very much for this introduction, and thank you for inviting me to talk today. It is my pleasure to be here to share with you all some of my recent work on the distributional and intertwining versions of LS category and topological complexity. So let me start off by giving a brief outline of this talk. This talk is divided into roughly three components. In the first part, I'll begin by discussing the classical definitions of LS category and topological complexity, and then I will use them to motivate the definition of the new distributional versions of these invariants. Then the second part of this talk is based on one of my recent projects on computing distributional category for some general classes of closed manifolds. So in this part, we'll just see some general results and examples. And in the third part, I'll discuss the intertwining versions of LS category and topological complexity, which are some new probabilistic versions that were recently developed and studied. So I'll try to give their interpretation in terms of motion planning, discuss their theory, and compute them for some manifolds. So let's start with the first part. And let me begin by recalling the notion of sectional category. So of course, most of us here know the definition that given a fibration P from E to B, its sectional category or ccat of P is just the smallest integer n such that the base space can be covered by n plus one number of open sets over each of which there exists a section of the fibration P. So this notion was called Schwarz genus earlier because it was introduced by Schwarz, but James started calling it sectional category. Anyways, we know that sectional category is a homotopy invariant of fibrations, and the classical notions of LS category and topological complexity can be recovered from this notion of sectional category of fibrations. So let us look at LS category now from that perspective. We start with a pointed space x naught with a base point x naught. And by capital P naught of x, we define the based path space of x. So this space has those paths whose endpoint is the base point x naught. And on this space, we define by a little p naught a fibration that evaluates every path at its starting point. Then the Lusternik-Schillmann category of x, denoted by cat of x, is just defined as the sectional category of this fibration p naught. Here is the classical definition of LS category from the 1940s. That category is the smallest integer n, such that x can be covered by n plus one number of open sets that are all contractible inside the space. Similarly, one can recover the notion of topological complexity from the general notion of sectional category. So for that, we fix an index m, and we define a fibration pi m from the full path space to the product space xm. And this fibration evaluates each path at m number of equally spaced timestamps between 0 and 1. So it evaluates the path at time t equals to 0, then at t equals to 1 over m minus 1, then at t equals to 2 over m minus 1, all the way to t equals to 1. Then the mth sequential topological complexity of x, denoted by tcm of x, is defined as the sectional category of this fibration pi of m. So I must say that for m equals to 2, this is the classical notion of topological complexity of a space, which is just denoted by Tc of x, which was introduced by Michael Faber with motivations coming from topological robotics. And then for higher m, this was extended in a natural way by Yuli Rudyak. Okay, now let me turn towards a characterization of sectional category in terms of some fibrations, so that I can use that interpretation to motivate the definition of the new distributional invariants. So we start with a fibration P from E to B, and we take the iterated fiber-wise join of k copies of E along this fibration P. So this is the space whose elements basically are formal ordered linear combinations such that the weights add up to 1. and P of EI is equal to P of EJ for any EI, EJ appearing in this linear combination, because we are taking the fiber-wise join. And on this space, one can define in a natural way a fibration that sends to any such linear combination to P of EI for any index I corresponding to which the weight lambda I is positive. So for any EI that actually appears in this linear combination. With these notations, one can give a characterization of a sectional category. So it turns out that sectional category of the fibration P is at most n, if and only if the n+1th fibration admits a section. This is the classical theorem of Schwarz, and basically in the notations of the previous slide, we are taking k equals to n+1 over here. So this means that sectional category is just the smallest integer n, such that each element of the base space is mapped to an ordered linear combination of at most n+1 weighted elements EI, such that P of EI is equal to X for each I appearing in the linear combination. And I would like to specify that these spaces E and B are very nice spaces. They are compact metric ENR spaces. So this theorem holds. By looking at this interpretation of sectional category, we think about defining a new invariant which assigns to this fibration P the smallest integer n, such that each element of the base space is now mapped to a formal unordered linear combination of the above kind. So instead of mapping it to ordered linear combinations, we now want to map it to unordered linear combinations having at most n+1 weighted elements. And this kind of motivation gives rise to this new invariant, which we would like to call as distributional sectional category. So before I formally define it, let me just fix some notations. Given a metric space Z, let Bk of Z denote the space of probability measures on Z having support at most K. And let us assume that this space has the metric topology coming from the Levy-Prokhorov metric or the Wasserstein distance metric. So if we have a nice vibration from E to B, then we can apply this functor Bk fiber-wise on E to obtain this space, which I would like to denote by E subscript K of P. So this space is basically just the union over the points in the base space of Bk applied to the fibers. And the elements of this space are just measures whose support are contained in the fiber of some element. And on this space, we define in a natural way a map that sends any such measure to that element in whose fiber the measure of the support is contained. So this is a natural definition, and it turns out that this map is not just continuous, it's in fact a Hurewicz vibration. So with these notations, we define the notion of distributional sectional category. So given a fibration P, its distributional sectional category denoted by dcat of P is the smallest integer n, such that the n+1th fibration admits a section. Here we have Bn+1 of P. So in the notations of the previous slide, it is just K equals to n+1. And just like the notions of LS category and topological complexity are recovered from the classical notion of sectional category, here, given this general notion of distributional sectional category, we would like to recover some special invariants. So in that direction, with Dranishnikov, we defined the distributional LS category of a space X, which will be denoted by dcat of X, to be the distributional sectional category of this the fibration P0. We recall that this fibration is from the based space and it evaluates the paths at its starting point. And similarly, for each M, one can define the mth sequential distributional complexity of X, denoted by dTCM of X, to be the distributional sectional category of the fibration pi M. So basically, these distributional notions of category and complexity are recovered from the notion of distributional sectional category in exactly the same way as the classical notions of category and complexity are recovered from the notion of classical category, the sectional category. And we can see that this definition of distributional sectional category is very similar to the definition of the classical sectional category when we consider the equivalent, when we consider the characterization of Schwarz. Um, so let us look at some facts about these invariants. First, we see that dcat is a homotopy invariant of fibrations. That's not very difficult to prove. And in fact, dcat is a lower bound to ccat, because in the case of ccat, we are dealing with spaces whose elements are formal ordered linear combinations. If we just forget about the order, then we end up with unordered linear combinations satisfying the same property. And those are the elements that are involved in the spaces which are considered in the definition of dcat. So distributional categories are lower bound to classical category, and distributional complexities are lower bound to the classical complexities. At this stage, I would like to mention that while we were developing these notions with Zhernishnikov, Knudsen and Weinberger independently developed some related probabilistic notion called as analog sectional category, which is also a lower bound to the classical sectional category, and which gives specific invariants called as analog category and analog complexity. So in the last talk in this series of seminar, Dr. Weinberger talked very nicely about these invariants. So I'm not going to say much about them, but I would just say that these notions are very much related to our notion. And in fact, there is only a subtle formal difference in the definition of these notions, which led Knudsen and Weinberger to conjecture that their notions are same as the distributional notions. And in that direction, one can show without much difficulty that distributional invariants are actually lower bound to the analog invariants, which are of course lower bound to the classical invariants by definition. Okay, so now that I have introduced these distributional invariants, let me focus on the specific invariants dcat and dtcm. And before we proceed, the first question, of course, is to check if the distributional invariants are any different from the classical invariants. Do we have examples of spaces where DTCM is not the same as TCM for each M? And it turns out the answer is yes. For that, we consider the case of real projective spaces, RPN. So we know in the classical case that LS category of RPN is just N. And due to this beautiful theorem of Farber, Tabachnikov, and Uzbinski, we know that topological complexity of RPN is equal to its immersion dimension when n is not equal to 1, 3, or 7. And in the other three cases, it's just equal to the dimension n. Surprisingly, in the distributional case, we have very easy answers. It turns out that distributional category and distributional complexity of RPN is equal to 1 for all n. So there is no dependence on the dimension. We have this constant value. And this is actually the first example that distinguishes the distributional theory from the classical theory. And interestingly, Knudsen and Weinberger also came up with the same example in their paper. So let me give a brief sketch of the proof of this equality. And basically, the idea is to prove that the number 1 is an upper bound to DTC of RPN. So to see that, let's consider this pictorial proof. Two different points x and y in RPN are just lines x and y in Rn plus 1 centered at the origin that make angles alpha and beta with each other. And a path from x to y in RPN is same as the rotation of the angle, rotation of the line x to the line y via a certain angle. So in Rn plus 1, there are two canonical ways of rotating x to y. One is via the angle alpha, and the other is via the angle beta. And let us call these rotations R alpha and R beta. So corresponding to this ordered pair x comma y, we assign we have this unordered linear combination, beta over pi R alpha plus alpha over pi R beta. And it's not difficult to see that this depends continuously on the ordered pair x comma y. And of course, just for the sake of completion, let me mention that if the points x and y are equal, then we do not rotate at all, and we just have the constant rotation by the angle 0, for example. So this assignment is continuous on the product space RPN cross RPN, And therefore, we can deduce that DTC of RPN is equal to 1. And this proof does not depend on n. So this proof works for each dimension, and therefore we have our equality. In fact, this equality can be generalized to an inequality in the case of sequential distributional complexities. One has that for each m, DTC_m of RPN has a uniform upper bound, namely 2 raised to the power m minus 1 minus 1. And that's also not very difficult to show. It's just following the definition. Okay, now the idea is to compute these invariants dcat and DTC for many spaces. And to do that, of course, we would need some lower bounds, just like we have in the classical theory. So with Zvanishnikov, we proved that for a finite CW complex, its rational couplength is a lower bound to its distributional category, and its rational zero divisor couplength is a lower bound to its distributional complexity. And I would just like to recall that zero divisor couplength just means the couplength of the kernel of the homomorphism delta star, which is induced in cohomology by the diagonal map delta. So this theorem should be compared with the theorem in the classical case, where we have that couplengths with respect to coefficients in any rings are lower bound. Here, that's of course not true. As we can see from the example of RPN, Z2 couplengths are not the lower bounds, for example. But it turns out still the rational coupling is a lower bound. Similarly, for sequential complexities, one can say that if we have a finite CW complex that has rational cohomology in some positive degree, then its mth distributional complexity is at least m minus 1. And the technique of the proof of this theorem can be used to give much better lower bounds for specific manifolds. Namely, if we take the products of spheres, then we can show that DTCM of this product of spheres is same as its TCM value, because this number can be recovered, this number can be obtained as a lower bound to DTCM. And of course, this is an upper bound due to the classical value. Similarly, if we have closed orientable surfaces of genus bigger than 1, then it turns out that their DTCM value is also same as the TCM value for each m. And we are just using this technique of this theorem to obtain better lower bounds. These numbers are obtained as lower bounds. So the lower bounds and the upper bounds are same, and therefore we obtain these values. Computations for dcat are even simpler. So just by using the rational couplings, we can say that for products of spheres, closed orientable surfaces, and complex projective spaces, the dcat values are equal to the respective cat values. And this example kind of motivates a question on what general classes of closed manifolds do the cat and the dcat values agree. So the examples that we have till this point are very specific. They are specific spaces, but it's natural to wonder if there are some general classes of manifolds on which the dcat and the cat values agree. And this question kind of motivates the second part of this talk, which is on the dcat of closed manifolds. So in this part, basically, I'll mention some classes on which the dcat and the cat values agree. And let us start by looking at the class of aspherical manifolds. So given a finitely generated discrete group gamma, since dcat is a homotopy invariant of spaces, one can define dcat of gamma to be the dcat of its classifying space. So one can obtain this dcat as a group invariant in the case of discrete groups. Some computations in this direction for finite groups are as follows. It turns out that dcat of Z mod 2 is 1. Knudsen and Weinberger showed more generally that if we have any finite group gamma, then its dcat is at most the order of the group minus 1. And then Zvanishnikov showed more recently that dcat of Z mod P is equal to P minus 1 for all primes. And these examples kind of raise a question: is there an algebraic description of dcat of gamma? what is dcat of gamma algebraically? And this question is, of course, motivated by this classical theorem of Eilenberg and Gania, which describes the classical LS category of gamma completely. So we know that for a discrete group gamma, its LS category is equal to its cohomological dimension. And it is natural to wonder if such a nice description holds for dcat of gamma as well. So it's easy to see that it's not always true that dcat of gamma is equal to the cohomological dimension, because we just saw that dcat of z mod p is p minus 1. But of course, its cohomological dimension is infinite. So an analog of this theorem is not always true, at least when the groups have torsion. In that direction, interestingly, Knudsen and Weinberger showed that for their invariant analog category, acat of gamma is equal to the cohomological dimension as long as the group gamma is torsion-free. So in a very nice result, Knudsen and Weinberger obtained a version of the Eilenberg-Gania theorem for analog category when the groups are torsion-free. And it's not difficult to see that their specific proof actually works for distributional category as well. So basically what we have is that if gamma is a torsion-free discrete group, then dcat of gamma is equal to the cohomological dimension, which is of course equal to its category. And I would like to point out that this result was one of the main motivations for this project. And a simple corollary of this fact is that if we have closed aspherical manifolds, then their distributional category is equal to their classical category. Now let us look at a slightly more general class of essential manifolds. So let me recall that a closed manifold of dimension n is called essential if there exists a map from the manifold to the classifying space of its fundamental group that induces an isomorphism of the fundamental group, and that this map cannot be deformed into the n-1 skeleton of the classifying space. So some obvious examples of these manifolds are aspherical manifolds, because then F can take in just to be the identity map. There are several equivalent definitions of essential manifolds. The one most useful for our purpose is the following, that a manifold is essential if and only if its LS category is equal to its dimension. So basically, the LS category of essential manifolds is completely determined. And it's natural to wonder if one can determine the distributional category of essential manifolds in a similar way. It turns out that it's not always true that distributional category of an essential manifold is equal to its dimension. I mean, we can easily see it using the example of RPN, which are essential manifolds, but their distributional categories are all one. The distributional category is one in each dimension. So an analog of this theorem is not true. And therefore, we can ask the question, for what essential manifolds is it true that the distributional category is equal to the dimension? And that question kind of encourages us to look at the class of essential manifolds whose fundamental group are torsion-free, because we had a counterexample in the case when the fundamental group had torsion. So let us look at essential manifolds with torsion-free fundamental groups. So let us fix M, an essential manifold of dimension n, and let pi be its torsion-free fundamental group. Consider this evaluation fibration, P naught, from the based path space of the classifying space to the classifying space. And given this fibration, we define the nth fibration, Bn P naught. So this fibration was already defined when we discussed the notion of distributional sectional category. We did it from the fiber-wise construction. So we have this nth fibration, and it follows from the work of Jonishnikov that the fiber of this fibration is n-2 connected. So basically this fibration admits a section to its n-1 skeleton, which means that the primary obstruction to a section of this fibration sits in the nth cohomology. So let us denote that primary obstruction by kappa n, which is a cohomology class of degree n. Let us say that this manifold satisfies the cap property if the cap product of the image of the fundamental class of the manifold with this primary obstruction is non-zero. So here kappa n is this primary obstruction of degree n. F is a classifying map that does not deform into the n-1 skeleton. F star is the map induced in the nth homology, and the square bracket M is just the fundamental class of M. So if this cap product is non-zero, let us say that M satisfies something called as the cap property. So this cap property we are defining because we want to obtain certain results in a certain way. And let us recall that our motivation was to find essential manifolds whose distributional category was equal to their classical category, which is equal to their dimension. So now with this cap property, we are in a position to do that. It turns out that if we have an essential manifold having torsion-free fundamental group that satisfies the cap property, then its distributional category is equal to its classical category, which is of course equal to its dimension. The proof of this proposition is not difficult. It's based on obstruction theory, and the cap property hypothesis over here really helps a lot in the proof. So I'll not mention the proof, but I'll rather discuss some of the applications and corollaries of this proposition and show how we can get some new and interesting computations of dcat for essential manifolds. So one special case is that if the essential manifold is such that the classifying space of its fundamental group is itself a closed manifold of the same dimension, then the distributional category is equal to the category. This holds because if the classifying space is a manifold of the same dimension, then due to Poincare duality, the cap property is satisfied, and therefore we can just appeal to the proposition. I would like to point out that in the case of this corollary, actually what happens is this primary obstruction kappa n is non-zero, and it's not difficult to show that f star of m is also non-zero. So because of Poincare duality, this turns out to be non-zero, which is not difficult to show. Okay, and of course, this recovers the result that for aspherical manifolds, distributional category and classical categories are the same. So this corollary, the first corollary, is kind of a new result, and I would like to show that this result actually gives us some computations. So for that, let me discuss the class of symplectically aspherical manifolds. Let M omega be a closed symplectic manifold of dimension 2n. Corresponding to omega, there is this de Rham cohomology class denoted by a bracket omega, which sits in the second cohomology. And let us assume that the nth power of this class is non-zero. So of course, corresponding to M, we have this Hurewicz homomorphism from the second homotopy group to the second homology group. And we say that this M omega is symplectically aspherical if the composition of this cohomology class with the Hurewicz map is trivial. Some obvious examples of such manifolds are those symplectic manifolds that are aspherical in the canonical sense, that are aspherical as CW complexes. Because if M is aspherical, then pi 2 of M is of course 0. So this composition is trivial and the condition is satisfied backwardsly. These symplectically aspherical manifolds are actually well-studied objects in topology and geometry, and in particular, they are essential. So basically, we can use our corollary for essential manifolds to get some computations for dcat of these symplectically aspherical manifolds. But to show that we can get some new computations, we should be able to calculate dcat of some non-aspherical SA manifolds. Because for aspherical manifolds, we already know the answer, that dcat is equal to the category. So actually, these computations can be done in some cases. It follows from the work of Kedra, Rudiak, and Tral that there exists a closed SA manifold of dimension 4, whose fundamental group is Z4, but whose second homotopy group is non-zero. So this manifold is not aspherical, but it is SA. And since the classifying space of its fundamental group is the 4-dimensional torus, we can use our corollary and say that its distributional category is equal to its dimension, which is equal to 4. More such computations for SA manifolds can be obtained. Specifically, we can calculate the dcat of some special branched coverings of some SA manifolds using the classical results of Robert Gompf. But let me just move on to the next part of the next section of this part. Let us now discuss the problem of determining dcat for connected sums. So in the case of classical theory, there is this famous theorem of Zhonyshnikov and Sadikov that completely determines the LS category of connected sums of closed manifolds. So it says that category of connected sum is equal to the maximum of the category of the summits. And we ask if the distributional category of the connected sum can also be described in a similar nice way. Basically, we ask, is it true that distributional category of the connected sum is also equal to the maximum of the distributional category of the summands? It turns out that that's not always true. An analog of this formula does not hold for dcat. And we have example in both the non-orientable and the orientable setting. We know that dcat of RP2 and RP3 are 1, but it turns out that dcat of connected sum of two copies of RP2 and dcat of connected sum of two copies of RP3 are both not 1. They are at least 2. So this equality does not hold for dcat. And therefore now we ask, okay, what are the manifolds for which we have this connected sum formula for dcat? So we saw a counterexample in the case of essential manifolds that had torsion in their fundamental group. So it's natural to now restrict to the class of essential manifolds whose fundamental group are torsion-free. When we consider such manifolds, we actually get some results. So this is perhaps the main result from this project, that if one of the summands is essential with torsion-free fundamental group, and if the summand satisfies the cap property, then the distributional category of the connected sum is equal to the maximum of the distributional category of the summands. Again, this cap property is that the cap product of the image of the fundamental class with the primary obstruction is non-zero. The proof of this theorem is by obstruction theory. And basically, we use the result of Knudsen and Weinberger, and we use a characterization of distributional category of continuous maps. And then using some technical details, we can arrive at this result. But I would skip discussing the technical details because perhaps it will be more interesting to look at the corollaries and applications of this result in a broader sense. So one special case of this theorem is that if the summand is essential such that the classifying space of its fundamental group is itself a closed manifold of the same dimension, then distributional category of the connected sum is equal to the dimension. And of course, because of Poincaré duality, the cap property will be satisfied in the case of this corollary. And perhaps a more elegant corollary is that if one of the summands is aspherical, then distributional category of the connected sum is equal to the distributional category, is equal to the maximum of the distributional categories of the summands. So this corollary is actually interesting, and it gives us many new computations of dcat. Let me highlight one of its applications in a more general setting of closed three manifolds. So we know that the LS category of closed three manifolds is completely determined in terms of the fundamental group of those manifolds due to this amazing theorem of Gomez-Larrañaga and Gonzalez-Acuna. It says that if the fundamental group is trivial, then category is 1. If the fundamental group is free but not trivial, then category is 2. And if the fundamental group is not free, then the category is 3. And this theorem was also proven by Opria and Rudyak using the notion of category weight and detecting elements. So we now wonder if the distributional category of closed three manifolds can also be described in such a nice way. And the answer is yes, for the most part. It can be shown that if the manifold, if the closed manifold is such that its fundamental group is torsion free, then its distributional category is equal to its classical category. using our corollary of aspherical summand and some other results, one can show that. So let me just go over this result. What we have is that if the fundamental group is free, then distributional category is same as the classical category. It's one or two depending on if the fundamental group is trivial or not trivial. But when the fundamental group is not free, then we have to consider a subcase when the fundamental group is additionally torsion free. And what happens in that case is that if the fundamental group is not free but torsion free, then in the prime decomposition of M, there exists an aspherical summand. So we can use our corollary from the previous slide and conclude that the distributional category of such a manifold will be equal to its dimension, which is 3 over here. So distributional category of closed 3 manifolds having torsion-free fundamental group is completely determined. But when the fundamental group has torsion, then we really don't know what this distributional category should be. Interestingly, the answer can be 1, the answer can be 3. So unlike the case of the classical category, we do not have a constant answer, and there is hardly any progress in this direction as of now. So this case is wide open when the fundamental group has torsion. Okay, now that we have seen enough about distributional invariants and we have explicitly computed distributional category for some closed manifolds, let me move to the third part of this talk and discuss the intertwining invariants, which are some recent probabilistic invariants which were defined and studied. And let me start off by giving a motivation for these invariants in terms of a certain motion planning problem. So let us consider this motion planning problem. Let us consider that we have an advanced robot that has to move from an initial position X to a final position Y. And in this motion, the robot is allowed to break into some pieces such that its pieces travel from the initial position to the final position. So the robot has to travel from X to Y, but it is allowed to break into some pieces at X and travel as smaller pieces to Y. It does not need to travel as a whole. This kind of idea could be more clear from this picture. So we have, so the system breaks at 4 pieces, say, at the initial position. All of these pieces travel independently to the final position, and upon reaching the final position, they just recombine to form the system. So this is this kind of breaking and reassembling kind of motion. It turns out that the invariant distributional complexity that we defined earlier has to say something about measuring the complexity of such a motion. More precisely, dtcx gives the minimum value n, such that given any pair of positions x and y, the system can travel from x to y by breaking into at most n plus 1 number of pieces that travel independently. And similarly, for the sequential motion, one can interpret dtcm in a suitable sense of repeated breaking and reassembling of the system. So this motion planning problem that we considered, it has a big restriction that upon breaking, the pieces travel independently between the positions. But what if we remove this restriction? What if we do not require the pieces of the system to travel independently? Rather, we allow them to suitably interact with each other while they are in the motion. So let me make that idea more precise. During the motion, let us allow the pieces of the system to merge with each other and to split into differently weighted pieces while they are traveling between the initial and the final position. So let me just give a sketch of this idea. Basically, the system again breaks into finitely many pieces. The pieces are this time allowed to merge with each other. So some of the pieces merge and then further split. Some pieces just split into something, and then the splitted pieces merge into some other pieces. And then these pieces travel as paths to the final position where they reassemble. So this is this kind of intertwining motion because the pieces can sort of intertwine with each other. They are allowed to interact with each other. So in the previous scenario, when the pieces had to travel independently, it's easy to see that one can describe such a motion by a unique collection of unordered paths of the pieces. But in this case, where the pieces are allowed to intertwine with each other, there are multiple collections of paths corresponding to the pieces of the system that give the same motion. So let me just give an example. Consider that we have this output motion in black color, which looks like figure 8. So the system breaks into two pieces at the initial position. At some random timestamp between t equals to 0 and t equals to 1, these pieces merge with each other, and then they again split into two pieces. So this is the motion that we have. Of course, one collection of paths that describe the motion of these pieces is this collection of the yellow and the blue path, which share this point at the time t naught. But then one can define another collection of paths that has the green path and the red path. Here, this green path is just the join of the upper part of the yellow path and the upper part of the blue path. And this red path is just the join of the lower part of the blue path and the lower part of the yellow path. So we see that these two different unordered collection of paths can actually describe the same motion. So since different collections give the same motion, the idea now is to measure the complexity of this motion planning by looking at the image of the system's motion rather than looking at the paths that describe that motion, which we were doing in the case of DETC, distributional complexity. We can't do that here because there are multiple collections of paths that give out the same motion. So this is the general idea about intertwining motion and how to possibly approach to measure its complexity. And let me give a mathematical formulation of that idea. So before I do that, let us first recall that for sequential distributional complexity, DTCM, DTCM of x was the smallest integer n such that there was a continuous map from the product space xm to the n plus 1th measure space of the path space. And this map was, of course, a section to the n plus 1th vibration, because we defined DTCM as the distributional sectional category of this vibration pi of m. So now for intertwining motion, one thing that we see is that we first have a natural map from the measure space of the path space to the path space of the measure space. Let us call this natural map capital phi k. So for the intertwining motion, we are interested in this space now, the path space of the measure space. And specifically, we are interested in those paths in this space that have a pre-image under this map. So for convenience, let us give a name to those paths. So let us call a path in the path space of the measure space as resolvable if it has a pre-image measure in this measure space of the path space under this natural map capital phi of k. With these notations and terminology, now we are in a position to define the notion of intertwining complexity. So for each m, the mth sequential intertwining complexity of x, which we denote by ITCM of x, is the smallest integer n for which there is a continuous map from the product space xm to the path space of the n plus 1th measure space. And this map is such that, number one, each path is resolvable. And number two, when the path is evaluated at time I minus 1 over m minus 1, it gives out delta xi, where delta xi is just the Dirac measure supported at the point xi. So let me go over this definition. What we have now is that we want a continuous map from the product space to the path space of the measure space, as opposed to the situation of DTCM, where we had a map from the product space to the measure space of the path space. So now in intertwining motion, we are coming one level down. We want a map over here. So this is this map. And of course, we want these paths to be resolvable. So we want these paths to have a pre-image under this map. And this condition that the path when evaluated at I minus 1 over m minus 1 gives delta xi, this is a natural condition that we have in the definition of classical sequential complexities and distributional sequential complexities as well. So this condition should not be a surprise. And the reason we call this invariant intertwining complexity is that it turns out that this invariant has something to say about measuring the complexity of the intertwining motion that I described earlier. So ITCM seems to give the minimum value of n such that given any sequence of m positions in the configuration space, the system can move between those positions by breaking into at most n plus one number of smaller pieces that are allowed to suitably intertwine with each other. So this notion of intertwining complexity has some interpretation in terms of a certain intertwining motion planning for some advanced systems. So this was the rough interpretation and motivation for defining these invariants. But theoretically, the major difference or perhaps the motivation is that now we want a nice map from the product space to the path space of the measure space. And with this idea in mind, one can define a cousin invariant called as intertwining category to go with intertwining complexity. So we start with a pointed space xx naught, and we define its intertwining category denoted by I cat of x to be the smallest integer n, such that there is a map from the space to the based path space of the measure space. And we require that each path h of x is resolvable, and its starting point is the Dirac measure at the point x. So this definition of intertwining category is very similar to the definition of intertwining complexity. We need resolvability, we have such a condition, and we have a map to the path space of the measure space. So similarly here, we have a map to the based path space of the n plus 1th measure space. Before I say more about these invariants, let's just make some quick observations. From the definition, it follows that intertwining category of a space is 0 if and only if the space is contractible. And intertwining category is a lower bound to the distributional category. This just follows from the definition. So basically for RPN, intertwining category is 1 because RPN are not contractible and their distributional category is 1. So this equality is obvious. Now let us look at some theoretical aspects of these intertwining invariants. First, we see some homotopy theoretic properties. These invariants satisfy most of the nice properties as we would expect. They are homotopy invariants. ITCM reacts with ICAT of products of X in a nice way. And in fact, the sequence of these intertwining invariants is also a non-decreasing sequence, just like we have in the classical and in the distributional case. And if we have a path-connected topological group, then intertwining category and intertwining complexity agree. So none of these properties should actually be a surprise. But before we proceed with the theory, a natural question to ask is, are these intertwining invariants any different from the classical invariants? Do we have examples of spaces X for which the sequential intertwining complexities are strictly lesser than the corresponding distributional sequential complexities? And the answer is yes. And for that, we look at this very interesting Higmans group, which is a finitely presented group of cohomological dimension 2. This group is torsion-free, and we know that its classifying space is a CW complex of the finite type, which is acyclic. So in a surprising computation, Dranishnikov showed that the intertwining category and intertwining complexity of this Higmans group is 1. And before I say any more about this equality, I would like to say that we can generalize this result for all the higher sequential intertwining complexities as well. So we have that for each M, ITCM of Higmans group is 1. And the proof of this is same as that of the Dranishnikov's proof. The idea is the same. And I will discuss this idea in a while. But let me just mention that this proves that intertwining invariants are different from the distributional invariants in general, because intertwining complexity of Higman group, which is 1, is strictly less than the distributional complexity, whatever that value may be. But we know that this value can never be 1. Now, let me give a brief sketch of the proof of this equality that ITC M of Higman group is equal to 1. The most important component of the proof is to show that there exists a continuous map from the product space to the path space of the iterated join. So here this star M of X denotes the M times iterated join of X. And we need to find such a continuous map such that each path, when evaluated at the timestamp I minus 1 over M minus 1, gives out the xi coordinate. So finding such a map in the case M equals to 2 is not at all difficult. It's trivial. But for bigger M, finding this map is tricky. We have to do some constructions, but ultimately we can arrive at such a map. And once we have that, the rest of the proof is not difficult. So if we know that since the classifying space of Higman's group is acyclic, we can use the theorem of Dold-Thom to conclude that its symmetric square is contractible. So if we let delta to be the diagonal inclusion of BH into the symmetric square of BH, and if we take M copies of this map, then because the symmetric square is contractible, this map can be extended to a map from the iterated join to the symmetric square. And once we have that, we can just take this composition where QM is this map on the top. P of F is just the map induced by this map F due to the path functoriality of the path space functor. And then we have this inclusion because the symmetric square of the space is embedded in the second measure space of BH. So basically, we can show that for each M, the mth sequential complexity of Higman group is at most 1. And therefore, we have the equality because Higman group is not contractible. The classifying space of Higman group is not contractible. This computation has various interesting implications. First, we know that in the classical case, for each M, the mth complexity, sequential complexity of Higman group is 2M. But in the intertwining case, of course, all the values are 1. So we have a constant answer. And this is more interesting because the distributional complexities of Higman group are unknown at this point. Also, we see that intertwining category of Higman group is 1, but its cohomological dimension is 2. So even for torsion-free groups, it's not true that ICAT of a torsion-free group gamma is equal to its cohomological dimension. So a version of the Eilenberg-Ghania theorem does not hold true in the intertwining theory, even for torsion-free groups. And this is remarkable because such a version holds true in the distributional theory. That was essentially the result of Knudsen and Weinberger. And finally, we see this result of Rudiak in the classical setting, which says that if we have a finite CW complex, which is connected but not contractible, then its mth sequential complexity is at least M minus 1. Such a conclusion does not hold true for ITCM because of the example of Higman's group. So the intertwining theory has some serious differences from the classical and the distributional theory. Now let us try to compute these intertwining invariants for some spaces in the last few minutes that I have for this talk. And of course, to do that, we would like to find lower bounds to the intertwining invariants. So in all the examples that we have seen till this point, the intertwining invariants turned out to be 1. So to show that the intertwining invariants are actually not trivial and they can potentially be useful, we would like to obtain the number 2 as a lower bound to intertwining invariants in various cases. So let us start by looking at intertwining category ICAT. We start off by, I'll just give a sketch of the main results and finally I'll show some computations. So we start off by showing that if the intertwining category is strictly less than 2, then the space X can be covered by 2 sets that are contractible inside the symmetric square of the space. It should be noted that these sets need not be open, these sets need not be closed, and these sets need not be contractible in the space X. They are contractible inside the symmetric square of X. Once we have this lemma, we can show that if we have a finite CW complex whose rational coupleth is at least 2, then its intertwining category is also at least 2. So to prove this theorem, we actually proceed by contradiction. We use this lemma, and then the remaining proof is essentially the same as the proof of the lower bound for the classical Ellis category. And I would like to point out that this theorem, in the case of distributional category, we had that the rational couplant was a lower bound to dcat. But in this case, all we can say is that the number 2 is a lower bound to icat as long as the rational couplant is at least 2. So this result is much weaker than the corresponding result in the distributional setting. But of course, it actually gives us some useful computations. So for orientable surfaces, complex projective square, product of two spheres, and closed simply connected symplectic manifolds of dimension 4, one can see that intertwining category is equal to 2, which is the same as the distributional category and the classical category value. Similarly, we would like to find lower bounds for ITC. We start off by showing that if ITC of X is strictly less than 2, then the product space X cross X can be covered by two sets that deform to the diagonal delta X inside the symmetric square of the product X cross X. So again, this deformation is not happening inside X cross X, it's happening inside the symmetric square. And by deformation, we just mean a homotopy, which starts as the inclusion, but which ends in the target space to which we are deforming the initial set. Once we have this lemma, in an analogous way, one can easily show that if we have a finite CW complex whose rational zero divisor couplant is at least 2, then its intertwining complexity is also at least 2. Again, we are not saying that the rational zero divisor couplant itself is a lower bound to intertwining category. We are only saying that the number 2 is a lower bound as long as the rational zero divisor couplant is at least 2. And there are some simple computations again. So for even spheres, product of two odd spheres, and for finite graphs whose Berry number is greater than 1, we see that the intertwining complexity is equal to 2. So for all these cases, ITC, DTC, and TC values agree. And finally, we can find a lower bound to ITCM in the same way. If we have a finite CW complex, which has rational cohomology in some positive degree, then its all sequential intertwining complexities have a uniform lower bound of the number 2. So here M is taken to be bigger than or equal to 3 because, if M is equal to 2, then we already have the answer over here by this theorem. So for the higher intertwining complexities, we again get 2 as a lower bound. And this should be compared with the corresponding result in the distributional case, where we had that the number M minus 1 was a lower bound to DTCM. Here, all we have that is the number 2. Here, all that we have is 2 is the lower bound to ITCM. So this result is much weaker. But a quick observation is that this hypothesis that the finite CW complex has rational cohomology in some positive degree, this hypothesis is necessary because of the example of Higmann's group, whose all intertwining complexities are 1. So this hypothesis cannot be dropped. And we have some obvious corollaries of this theorem, namely that if we have a closed orientable manifold or a closed non-orientable surface of genus bigger than 1, then all of its sequential intertwining complexities are at least 2. This is because these spaces, of course, have rational cohomology in positive degree. And this has this specific example that the third intertwining category of any odd sphere is 2. Because the number 2 can be obtained a lower bound from here, and it can be obtained as an upper bound due to the classical value of sequential complexity of odd spheres, which follows from the work of Ridyak. So finally, I would like to just point out that this computation, that ITC3 of odd spheres is equal to 2, it cannot be obtained by any other result that we know till now in the theory of intertwining category and complexity. So this corollary, which gives a lower bound, actually gives us some new computations. And that is all I wanted to discuss today. I think I'll stop here. Thank you very much for listening.
Thank you very much. This is a wonderful talk.
Thank you.
Okay. So let's, if anybody wants to ask questions, please go ahead.
I have a question, Ekansh.
Sure.
Do you know anything about how either distributional or intertwining category behave with respect to covering spaces?
Yes, that's a good question. So with respect to covering spaces, we have the same result in the distributional setting as we have in the classical setting, that distributional category of covering space cannot exceed distributional category of the base space.
Mm-hmm.
That's how we can calculate distributional category for non-orientable surfaces also. But in the intertwining category case, we do not know. I mean, I do not know if that holds anymore. So in particular, I do not know what is the intertwining category of the Klein bottle.
Mm-hmm.
Yeah. So.
Well, if no one else has I have another question. So for manifolds, let's say, we know there are certain Iwasi manifolds which don't obey the Gagne condition. If we look at, say, distributional or intertwining category for those manifolds, do they satisfy the Gagne condition, or is there a Gagne conjecture for these types of things?
Yes, that's also a very good question, because I was thinking about it. And no, the short answer is no. We do not have proof of an analog of the Gagne conjecture, and I do not have any counterexamples. But I would like to suspect that there could be a counterexample. In the distributional case specifically, say RP2 cross S1. Its distributional category could be 3. I really don't know. It's just a speculation. So if its distributional category is equal to 3, then it's a counterexample. And as I said, this is a closed 3 manifold whose fundamental group has torsion. So I don't really know much about it. But yeah, and I even know less in the case of intertwining category. So they are
okay. Thanks.
Well, I have another question. Anybody else has some question? Well, if not, let me pose my question. Let me just go back to the situation of real projective spaces, which are really very. This is amazing that these distributional and intertwining invariants are simple. So I was wondering if you have thought of similar results in the case of other Grassmann manifolds, Grassmannians, subspaces of not only lines, but say planes, spaces of subspaces of dimension 2, say.
I have not thought about that, but of course, that could be a natural direction to think about, because we have easy computations for real projective spaces, as you said. So one could expect to get new computations for Grassmannians, and we could expect to get differences. But I've not thought about it. I should think about it. Thank you for the suggestion.
Yeah, it's quite strange, no? But in the case of lines, you have only 2 ways of moving a line to the other one, and that's kind of the answer of why the reason
Yes.
why there is one. So if you could figure out how to move a plane to another plane in any kind of dimensions, maybe you could just
Yes. Yeah. I think I should think about it and then say something about that. Yeah, but I understand one could generalize that sort of idea and get something useful for that. Yeah, thank you for that suggestion.
All right, if there are no more questions, let's please thank again Ekansh for a magnificent All right, so Will, let's
Jesus, I'm not able to stop the recording. You'll have to stop it somewhere.
let me see if I can figure this out. Record computer. Phew. Ha. This is gonna be tricky because all the controls have changed.
Yeah.
And anyway, but let's just say goodbye and finish it
Yeah,
up.
I think that's the way to do it. Yeah.
Thank you very much.
Thank you, Ekansh.
Thanks again, Ekansh.
Absolutely. Thank you.